I write in detail what I get here, then I get the periods over A alpha. Let's denote them by A alpha big. The periods B alpha, denote them by B alpha big, and say Cm, which is integral between x1 and Cj, and xj of W, where j runs between 2 to R. So the dimension here, dimension of this space is going to be 2g, these coordinates plus these coordinates, the complex dimension, plus R minus 1. And if the number of zeros is equal to 2g minus 2, so all zeros are simple, then I get here 2g plus 2g minus 2 minus 1, which is exactly 4g minus 3, as it should be. Right? So that's the bunch of local coordinates on my space. Now, suppose I ask the same question as here. Well, let's take the basis of normalized holomorphic differentials on my Riemann surface and ask the question, so let's vary them with respect to A alpha, B alpha, Cj. What do we get? The easiest is, of course, to say what are the integrals with respect to these guys. And the reason for that is that these coordinates Cj are almost, well, the closest relatives of these coordinates here, of the branch points. Because I can introduce the natural flat coordinate on my Riemann surface associated to my integral. I just take those coordinates z such that dz is equal to w. Locally, I can always solve that. This is the coordinate which people use in Teichmüller theory all the time. And these ergodic people who study the geodesic floors in flat metrics on Riemann surfaces, they what did I want to say? I lost myself. Okay, so let's try to understand what should be the variational formulas with respect to these coordinates. So should I? No, that I'll try to keep for a while. Yeah. So I wanted to comment on variational formulas with respect to these guys. So if I introduce this flat coordinate z, then this flat coordinate, well, these are basically the integrals between the zeros of the one form W. In that context, in the context of Hurwitz spaces, the branch points were, well, say difference of two branch points is just an integral of the differential df between these two zeros, between two of its zeros. So these Cj's are exactly, well, the differences of the branch points. Then we can say freeze one of them, and like it's done here. You see, the first branch point, when we differentiate with respect, well, it doesn't make sense to differentiate with respect to x1. We differentiate only with respect to the difference. So we should expect basically that the formulas with respect to Cj's, they should essentially coincide with those which are written here, where df is substituted by W. And this is indeed the case. So let's take now, say, V alpha, and try to vary V alpha with respect to Cj, keeping, now I have to say something. D by d Cj of V alpha, keeping z of x constant. So V alpha of x. Now I have to say something about these coordinates z. And I started talking about that, but forgot what I wanted to say. So the coordinate z. Z is flat coordinate on L, and it's defined locally by equation dz equals w. So of course this equation defines my coordinate not uniquely, but what I can say from that if I take some coordinate covering of my Riemann surface by coordinates like that, then all transitional functions will be linear functions. Right? So this is so-called translational coordinate or translational structure on my Riemann surface. So to say that I choose z of x equals constant, I have somehow to choose this flat coordinate in the neighborhood of each point of my Riemann surface. How to do it? I can do it in many ways. For example, each flat Riemann surface. By the way, if I take the matrix, my Riemann surface with the metric module of w square, then what distinguishes this metric among all other metrics with conical singularities? What distinguishes this kind of metric is that it has trivial holonomy. So if I go around any loop, then I come back. The holonomy is trivial. It's clear that it's trivial around the zeros of w, around the conical points of this metric, because the conical angle is multiple of 2 pi, but also the global holonomy is also trivial. So essentially, this kind of Riemann surface is glued from cylinders. Now, I can also realize such Riemann surface in the following way. I can choose in the plane some polygon with such that its sides can be split in pairs, and each pair has coinciding length and is parallel. Right? Then I can make identification pairwise, and I get a Riemann surface with conical points. So, and it's that coordinate which we choose as a global coordinate on our Riemann surface. Because if we change, it's like the choice of the fundamental domain in Fuchsian uniformization. You can choose it in a different way, but once you choose it, you stay with that. So in this sense, we write here z of x equals constant. By the way, I should probably, before I write what I get here, before I write the answer, I should probably show the simplest realization of a Riemann surface equipped with holomorphic differential. In genus 1, if I have a Riemann surface of genus 1 and holomorphic differential, then I choose, of course, this coordinate z, well, such that w is equal to dz, and then I get a torus. I don't have any zeros of my differential. I just get two sides, side A and side B. So this is genus 1. No zeros, no problems. But genus 2, I get zeros and start getting problems. So the simplest picture which I can have here looks like that. I take two tori, one torus with the sides A1, A2, and A1, B1, and the second with sides A2, B2. And take here point 0 and point C2. I have only in genus 2 for the stratum H211. H211. I have one coordinate like that, two coordinates like that, and two coordinates like that. So I take two tori, one A1, B1. I take a torus with the sides A1, B1, another torus with the sides A2, B2. Take a branch cut here inside of the first torus between 0 and C2, and inside the second torus with the between 0 and C2, and glue them together. It's kind of pseudo covering of the torus. If my first torus coincides with the second torus, then I get a torus covering. If not, then I just have two different tori glued over the branch cut. Well, and then W is equal to dz. I assume that the z coordinate is the same here and there. And then, of course, well, in exactly the same way as in the case of the Hurwitz spaces, this one form has 0 here and 0 here, because the local coordinate in the neighborhood of 0 is square root of z. So dz has simple 0 there, and also here. So that's the example. Of course, that's a local picture with respect to the moduli, and there are various questions about the global picture which you get. For example, if C2 starts, well, increasing, and this branch cut becomes longer and longer and longer, or the size of the torus becomes smaller and smaller and smaller, etc. Also, if you merge these two zeros, if you consider the stratum H22, then the picture should be modified. But that's a generic picture which intuitively can be used to understand well, what's going on. And you see, when I differentiate, say, my holomorphic differential with respect to C2, I don't care whether this is a torus or that's a plane. Locally, in the neighborhood of this branch point, well, it's exactly the same as in the case of the Hurwitz space. So I can write exactly the same variational formula, which of course I can slightly modify to make it more uniform. I can write it like that: 1 over 2 pi a integral over the contour Lj star of w of xy the alpha of y. And I need something here, w of y. Now, what is this Lj star? There is a duality between this relative homology group H1 of W and the group H1 of the punctured sphere. When instead of taking the relative homology group, I just delete these zeros, and then the homology basis there would be just the absolute homologies plus contours around the punctures, not between the punctures like in the relative homology group, but around the punctures. And of course, there is a natural pairing between these two homology groups, the intersection index. So this Lj star, well, this star appears to the duality between these two homology groups. Then, of course, it's tempting to think that with respect to these two coordinates, two types of coordinates, we are going to have a similar formula. And this is indeed the case. So with respect to any zj, the alpha of x, when z of x is frozen, we get this formula: 1 over 2 pi a integral over Lj star. So you see here zj, we get integrating w along the contour Lj, and here I get Lj star of w of xy, the alpha of y divided by w of y. You see, well, when you look at this formula, if you read, for example, modern papers either on Witten equations in integrable systems or on Seiberg-Witten equations in supersymmetric Young-Mills series, somehow something looks very familiar here. You see, they always take some object, differentiate with a period of one integral, and in the right-hand side, they have a period of a different object over the dual period on a Riemann surface. Say, if well, typically it's easier. Say in Seiberg-Witten you differentiate with respect to the period of some integral and get another period of the same integral. Here it's a bit different. Here the differentials which you integrate in the left and in the right hand side are different, but still there is quite some similarity. And it's of course not a coincidence. Essentially, all these tau functions I am going to talk about are the partition functions of appropriate quantum field theories, like isomodromic tau function in particular. So the fact that these equations, this type of equations appear, is not just a coincidence. But before coming to more detailed discussion, let me just, for the matrix of B periods. So if I take now this equation, integrate over cycle B beta, then this, I can forget about that. The matrix of B periods doesn't depend on anything, on any choice of local coordinate. It's just integral over Lj star of V alpha, V beta over W. And you see why I wrote this formula for the variation of with respect to the vector field. Because what happens here, you see, in that formula I had V alpha, V beta times vector field, integral over some contour. Here I have V alpha, V beta divided by one form. So 1 over 1 form I can understand as a vector field. So, and then I integrate it with respect to some contour. So it's the formula of the same origin. And how to derive the variational formulas with respect to these periods? Well, essentially, you see, if I look at this torus, I know everything if I just freeze A and start varying everything with respect to B. Then, of course, I know everything. I can take my one form. I know how the period changes because the period is just B over A. I know everything. When I look at this picture, well, essentially, locally, when I change A1, it's the same as in the case of genus 1. Everything else is frozen. Nothing happens here. Nothing happens here. The variation is completely local. And of course, I just derive the formulas right away. Essentially, I get when I say vary my holomorphic one form with respect to A1, then I get some one form with the jump on the B contour, and the one forms with jumps, they can be reproduced using Cauchy kernels, and essentially W is a Cauchy kernel, right? If I have some differential with jump on my Riemann surface, I integrate W over the contour where I have jump, and I reproduce this differential. It's elementary complex analysis. So these formulas one can easily justify. Good. So, okay. The last variation which I wanted to discuss is the Teichmüller variation, which is very closely related to this one. Because what is Teichmüller variation? Teichmüller variation is I take two Riemann surfaces and I am looking for the quasi-conformal map with smallest distortion, which maps one to the other. And Teichmüller theorem tells us that to do that, we have to choose an appropriate quadratic differential pointing in the direction of this second Riemann surface. And then how the deformation looks like. I take this quadratic differential. Let's consider the simple case when quadratic differential turns out by chance to be a modulus square for one form, of holomorphic one form. Then I introduce a global coordinate exactly like that, integrate this one form from some point to a point of my Riemann surface, and then I get a flat global coordinate, global quote unquote, And then the Teichmüller deformation looks like that. I stretch my Riemann surface in one direction with some coefficient and compress in the other direction with the same coefficient. Well, you can avoid compressing. I just want to keep the area fixed. That then you have to simultaneously. If you stretch it in one direction with coefficient k, then in the opposite direction you should stretch it with coefficient 1 over k. And this is how the Teichmüller deformation looks like. So from the point of view of these homological coordinates, well, if your Teichmüller deformation is given by the modulus square, by the square of this holomorphic one form, then the Teichmüller deformation would be just simultaneous multiplication of real parts of all homological coordinates with some coefficient, and multiplication of the imaginary parts with 1 over this coefficient. And if you open again any textbook on Teichmüller theory, then we find that, so picture number, variational formulas number 5. So 5 Teichmüller deformation. So take W to be W's small square. So then the Beltrami differential corresponding to the infinitesimal deformation in the direction of this W is known to be like that. It's W bar over W. So that's the Beltrami differential describing Teichmüller deformation. And then say delta mu of b alpha beta is supposed to be double integral over our Riemann surface of v alpha, v beta, w bar over w. Right? One can put wedge somewhere. Now, of course, a thing like that, we can use Riemann bilinear relations and rewrite a little bit, right? Because here we have two closed one forms. We can put it on the boundary, and from double integral we get a bunch of single integrals. And then using the chain rule and apply these formulas, we get the formulas coinciding with that. So if you use Riemann bilinear relations, then you send it to the boundary of fundamental polygon of L, then you get some set of line integrals. And of what? Which kind of line integrals I'm going to get here? I am going to get what, by the way? Oh, it's better to write it, to put wedge in a different place. Let me write it like that, wedge W bar. Then I get line integrals of the following type. See, W bar and integrals A alpha, B alpha, and integrals of V alpha, V beta over W. And you see the ingredients are the same as the ingredients we have here. So, of course, one should be accurate, because here this one form is not holomorphic, it's meromorphic. So when I apply Stokes' theorem to that, then I have to take the fundamental polygon of my Riemann surface, A1, B1, A1 to the minus 1, B1 to the minus 1, take out the zeros of W, x1, etc., xr, choose some. Well, I have to apply essentially the Stokes' theorem to the boundary of, well, of that minus these contours. And then I get the formulas which I get by application of chain rule to these formulas. Because essentially the Teichmüller deformation in terms of homological coordinates is just simultaneous stretching of all of them. So I get the same as chain rule applied to these formulas. So indeed there is pretty close relation of all that to the canonical business of Teichmüller deformations. So in the remaining 3 or 4 minutes, let me see whether it's a natural breakpoint, or I have to do something else. So you see, I think it's a good point to stop for today and then start tomorrow from describing the special Riemann-Hilbert problems corresponding to the interesting monodromy data, and then I will come to the determinants of Laplacians and describe the... Well, so essentially today's talk was technical preparation to what I'm going to do tomorrow. I didn't say anything not trivial today. It was just a textbook material, but tomorrow I hope to do better. Okay, thank you.
Communication or comment?